We talked about limits quite a bit. We haven't yet talked about asymptotes. And so here's a problem we had last time. F of x is x squared minus 3x over x squared minus 9. And a was equal to 3. Okay? And I did compute some limits last time. And I think the only difference is, what does that say that's different? Compute the limit as x approaches what? That's weird. What we had last time were things like 3 or negative 3, right? Maybe the first thing to do, if you have a graphing calculator, go ahead and punch that function back into the calculator. I'll get it up here in a second.
Something wrong.
Yeah, something's wrong. So let's see. X squared minus 3x over x squared minus 9. I'll put that in the y equals screen again because I want to see it. Oh, I need to change my mode or it's not going to happen. X squared minus 3x over x squared minus 9. Okay. So I'll go ahead and graph. Error. What did I type in wrong? Well, we need a 9. Thank you. All right. Let's try graphing that. Well, that looks different than yours. That looks like a good old echocardiogram or something. At least I'm still kicking. So let's see. Let me get the standard window. You guys have something that looks like that? Okay. And what we did last time was we talked about that this function, the limit does not exist at negative 3, but the limit did exist when a equaled 3. Well, now we're talking about something very different, and that is the limit as x goes to infinity. So let me punch up the paper here, and we're going to compare to the graph and kind of see what we learn. Okay. Limits and asymptotes.
Isn't that 2.2?
Yes, thanks. 2.2. So last time when we had this function, f of x is x squared minus 3x over x squared minus 9, when we wanted to compute some of these limits, one of the things that we did was we factored. Right? We factored. And that helped me to compute a couple of things. When I computed the limit as x approaches 3 of this function, well, if I just plug in a 3 right now, what would happen? If I just plug in a 3 right now, I'd get a 0 in the denominator, but I would also get, and that was an example of the indeterminate form. Made me think, well, maybe I can do something. In this case, what I can do is I can cancel the x minus 3's. I showed this last time, right? So we got a half. And so sure enough, when I showed you guys the table last time, we saw that the values do get close to a half as you get close to 3. Right? We saw that last time. So that was maybe one of our first examples of a limit. We also did the limit as x approaches negative 3 of f of x. So again, if I look at the limit as x approaches negative 3 in this factored form, well, let's see what would happen if I plug in negative 3. I'll get negative 3 times negative 9, right, over 0 times negative 6. So here I get 27 over 0, right? Is that okay? No, no good, all right? This, we know, is undefined. And what that implied was this limit does not exist. But I want to say one more thing about it. If you get a 0 in the denominator and you get something non-zero here, that actually means something about the graph. And what it means about the graph is you're going to have what's called a vertical asymptote. A vertical asymptote. Raise your hand if you've seen vertical asymptotes before, or some kind of asymptotes. I'm sure in college algebra you saw this at some point. All right? But in terms of knowing when they happen, it really has to do with the limit not existing and with getting a 0 in the denominator if you sub in. But I want to point out that's a notable difference from this. Here we got a 0 over 0. We were able to factor and compute the limit. Go ahead.
Does this mean any time that the limit does not exist that there will be an asymptote then? Or no?
No. We saw another example today of the limit not existing that looked like this. Remember? That's not an asymptote. This is what you might call a jump. An asymptote is where either the values grow without bound or they decrease without bound, and it kind of depends which side you're on sometimes, right? So those are different. But what I'm telling you is try this substitution principle. Take that a and plug it in, and if you get a 0 in the denominator but you get something non-zero in the numerator, look for this, okay? You have an asymptote. And you know, that's what this section is about, is asking, what do limits tell me about asymptotes? Now, I still haven't done the problem that I'm supposed to. The problem I'm supposed to takes this function and asks a different question. It doesn't ask, when does x approach 3? It doesn't ask what happens when x approaches negative 3. What the problem asks is, hey, let's compute the limit as x approaches what? Infinity. Now again, the function is x squared minus 3x over x squared minus 9. Okay? And what this is asking you is, hey guys, what happens when x grows without bound? Okay? So basically, what happens when x gets very large? Well, what often happens is you get what's called a horizontal asymptote. In this case, give me a large number. One of my favorites is 1,000. Because, what's 1,000 squared? 1,000 times 1,000 is? A million, right? 10 to the 6th. Would be a million minus 9. You know what that is? Pretty darn close to a million, right? And even the numerator, a million minus 3,000. That's pretty close to a million. Are you with me? You basically have a million over a million. What's a million over a million? You're pretty close to 1. What happens when x gets very large? F of x gets close to the number 1. And so we're going to say that the limit equals 1. We're going to say that the limit equals 1. And I'll have to show you more precisely how I know that. But you could see it graphically right away. Here. Take a look. Well, I guess maybe not yet. Not yet I can't see it. But if I, for example, go to the y equals screen, and if I graph the line y equals 1 and graph it, well, that's what you might have learned in algebra class as an asymptote. Do you see how the curve is getting closer and closer to that line? Okay? Now, you've seen this before, as I mentioned. Here. The next example I want to do that maybe you're more familiar with is this one. Y equals 1 over x. That's a classic example. Okay? And so what I'd like to do is graph it and what asymptotes does this have? Okay. Well, first thing I'm going to tell you is this. It's going to have a vertical asymptote. How do I get a vertical asymptote? Remember up above what I did. To get a vertical asymptote, I had to figure out what would make the denominator 0. And that was when we plugged in a -3. Well, what about this function? What makes the denominator 0? Go ahead, anyway. No? What do you plug in for x? 0, right? So we have a vertical asymptote when x equals 0. Well, that means that the y-axis is a vertical asymptote. But now the next thing we might do is for the horizontal asymptote, let's take the limit as x goes to infinity. That'll tell me what happens. And so when x gets really large, what happens to 1 over x? Right? Like what's 1 over 1,000? 1/1000th? That's really close to what?
0.
Really close to 0. You guys with me? So y equals 0 is my horizontal asymptote. All right? Now at this point you can start plotting some points, right? I could plot the point 1, 1. I could plot the point 2, what would it be? 1/2. If I put in a 10, I'm at 1/10. You can actually see the asymptotic behavior happening. What happens if I plug in a fraction? Give me a fraction. 1/2. What happens if I plug 1/2 in for x? What's 1 divided by 1/2?
2.
That's 2. So you're up here. See, when you plug in fractions, if you plug in 1/10, the output's 10. It grows without bound. You can really see these horizontal and vertical asymptotes. And on the negative side, same thing, but negative. This is called a hyperbola. But I think understanding that graph helps me when I go to understand this problem. So let me redo this limit problem. I want to compute the limit as x approaches infinity of x squared minus 3x over x squared minus 9. And what I'm going to tell you guys is we don't want to factor. We're going to do a different trick. We're going to divide the top and bottom by x squared. Watch what happens. You get the limit as x approaches infinity. Now what's x squared divided by x squared going to give me? 1. Minus. Now here I have 3x divided by x squared. Are you guys okay if I write that as 3 over x? Right? Because if I have 3x over x squared, what happens? The x's cancel, so you get 3 over x. Who's with me so far? Okay. And then in the denominator, what am I going to get? 1 minus what? 9 over x squared. Okay? So I have 3 over x in the numerator. I have 9 over x squared in the denominator. And now, here's the question. When x goes to infinity, what happens? Well, when x goes to infinity, what happens to this fraction? I just talked about 1 over x. 3 over x is going to behave the same way, isn't it? What happens to this thing? It goes to what? 0, right? What's 3 over a million? Pretty close to 0. Okay? What about 9 over x squared? What's that going to go to? 0. Right? If you put in a really large number that you're dividing by, you make the thing very close to 0. Again, understanding 1 over x is totally fundamental to understanding this one. We have to understand that these things approach 0 when x gets really big. And so what is this limit? 1 over 1. Right? Because it's 1 minus 0 over 1 minus 0. So what's it equal? 1. I told you it would. But here's a proof that it does. We saw that asymptote y equals 1. Here, we should try another one.
Will we always divide? When you pick divide by x squared, will you always divide by the largest?
Yes.
Okay.
Except that there's an even easier way to do it, and I'm trying to get at that to see if you see it. So we just did this, and we did this. Let's try 2 more examples and see what you think. All right? So in the first one, right, I mean, this is what you were asking me, is what would I divide by, right? Limit as x approaches infinity. What do you think you guys were going to divide by in the first example there? X squared, right? And actually for the second one I will also.
What did I?
We're just trying these 2 problems now. I'm about to work them out. So I wrote them on my paper. I'm going to go ahead and work out that first one. You guys told me divide by what? X squared. So this equals the limit as x approaches infinity. When I divide by x squared, what's it going to say? 2 plus, what would be next? 3 over x, 4 over x squared. And then I get 5 plus 6 over x plus 7 over x squared. Now, what's going to happen to all those fractions when x gets really big?
0.
They all go to 0. So the limit is 2/5. If I plug that into a calculator, what we would say is y equals 2/5 is the horizontal asymptote. Guys with me? Now, does every function have a horizontal asymptote? No. These do. These are what you might call rational functions. They're fractions. What's the fast way to come up with 2/5? Go ahead.
Well, if you have the same, if x is squared by the same number on the top and the bottom,
Yep.
it just ends up equaling the integers.
Yeah, so in this example, we have the same degree, like you said, top and bottom. numerator and denominator. And if that happens, to get the horizontal asymptote, all we really had to do was look at the leading terms. Right? We had 2x squared, we had 5x squared. So we know if we did all that dividing, it's going to be y equals 2/5. You guys see that? Here, what about this one? Do we have the same degree in this second example? No, we have a different degree. Right? So in this one, let's divide again by x squared. So this equals the limit as x approaches infinity. I get, let's see, what do I get? The numerator. 3 over x plus 4 over x squared divided by 5 plus 6 over x, I think, right? And if you work out what happens here, well, I get zeros in the numerator, and I get a 5 plus 0 in the denominator. What is 0 over 5? 0. And the fact that I got 0 is no coincidence. It again has to do with the degree. We didn't have the same degree this time. So let me write another fact. If degree of denominator is larger than y equals 0 is a horizontal asymptote. And that's exactly what we got this time. And I guess the only other possibility would be if the degree of the numerator is larger, right? Well, if the degree of the numerator is larger, you don't get a horizontal asymptote. You could have vertical ones, but you're not going to get a horizontal one. And we'll see examples of that also. All right? So let's see. Close that. I'm going to start taking examples from your book. Because again, this is applied calc, and a lot of what it seems like we did today was very much, theoretical examples. I'm going to give you this function that we actually played with on the homework, I think, this n of x. You got a question first?
Wait, what was that last thing you said? If the numerator is greater than the denominator, there's no horizontal asymptote? Is that correct?
Right. If the numerator has it bigger, then you're not going to have a horizontal asymptote. Now let's take a look at this problem. There's the function. If you have your books, you probably want to open up, actually. How many have a book with them? Okay. If you have it, go ahead and find these problems from section 2.2. So we're talking page 125 is where I'm seeing these. Marketing, advertising, budget. Okay. I guess really the function is 126. Okay. Page 126 is where this comes up. But I thought this would be a nice example for you guys. Okay. So let's go ahead and look at the actual page. So problems 46 and 48 are up here at the top. And it says in problem 46, again, don't read the whole thing. Go right to what it's asking. Determine limit as x goes to infinity of this function n of x. And interpret. That's my job. So I could tell you already what's going to happen, because the first part of this is the mathematics. Then the second part is where I have to start reading. Here's the function, guys. What's going to happen when x goes to infinity? Right, because the 750 over x is going to approach what? 0. So this n of x approaches 3,200, right? So to do this problem, all right, let me go ahead and write it out. So again, this is section 2.2. We're going to try problems 46 and 48. And the first thing they wanted me to do is compute the limit as x approaches infinity of this n of x. And the funny thing is, I haven't even read what it means yet. I just know I'm computing the limit of this function, 3,200 minus 750 over x. Well, that limit is 3,200. Okay? Now, it says to interpret. So what is our interpretation? This is where you have to read a little bit. All right? You have to figure out what x represents. You have to figure out what n of x represents and see if you can interpret. So talk to someone next to you about that for about 20 seconds, and let's see what we come up with.
Oh, okay. Excuse me.
I mean, this thing, in order to interpret it, you really need to know what the variables stand for, right? What does x represent? Okay, advertising dollars. What about n of x?
Devices purchased. Number of devices.
This is the number of devices purchased. And so how do you interpret this? Well, the limit as advertising goes to infinity. In other words, you go ahead and buy a Super Bowl commercial, right? You could spend as much money as you want. What'll happen? Yeah?
The number of devices purchased will approach 3,200.
It'll approach 3,200. So, as you spend more and more money on advertising, that's not the result I wanted as a business manager, is it? I figure if I spend more money, I get more sales, right? But why doesn't that happen? It's not that simple, is it? See, this is real life. As you spend more and more money on advertising, sometimes you may saturate the market, right? Maybe there's only 3,200 people that want that new math book that I wrote. I could put a Super Bowl commercial on, but no one really cares, right? Well, maybe there's 3,200 people that care. So if I reach them all, right? So I would say my sales, or my number, how about this? Number of devices purchased approaches 3,200. It doesn't mean you spend. So, do you want to spend infinite amounts of money? Not in this situation. There comes a point where you say, oh, wait a minute, that's enough, because I realize that spending more money doesn't yield many more purchased. Guess what? Question?
Well, when you put in a bigger number,
Yeah.
when you put in 800, it's actually less than 3,200. So wouldn't it be like the more money you spend on advertising, you're going down?
Let's see. Let's see. That's interesting. So you're giving me some actual numbers. This is actually a good idea. Here, let me get the calculator. And so if I take, for example, 3,200 minus 750 divided by, and you can put whatever you want in for X, right? X is the amount of money you spend on advertising. So if I spend 25 bucks on advertising, because I get out a little flyer in some math magazine, right? Well, I'm going to sell 3,170. How much does a Super Bowl commercial cost nowadays?
$1 million for 30 seconds.
$1 million? I thought it was more than that.
At least in
I mean, am I out of line if I write that, guys? That'd be a discount if I got that for my Super Bowl commercial. Let's see what that is. Well, it went up, or like you said, when you put in 800, it went up, but very slowly, right? The graph is the horizontal asymptote. If you wanted to sketch a graph of this, right, there would be a horizontal asymptote where? At 3,200. So, you know, the number purchased, as x increases, the number purchased is going up, but it's so close, you know, it won't go above 3,200 here. You guys follow? Now, what about number 48? 48 says, graph the model in this viewing window. Use the graph to estimate an interval that would result in n of x being between 2,700 and 3,000. All right. So now this takes a little bit of work, and so I thought I'd show this off a little bit. Let's go to the y equals screen, and let's replace what's there with our function. So my function is 3,200 minus, and now I have 750 divided by x. So there's the x button. I don't want y equals 1 anymore. I'm going to get rid of that. Now if I press graph, I don't see anything. Again, it gives me a window. It says, let's use the window. Well, it says 0 and 40. Those are the x values, right? Let's spend between 0, and these are thousands of dollars, huh? 0 and 40,000. Yeah, so I should really correct that on my sheet. These are thousands. Okay? Thousands of dollars. That sometimes makes a difference in the interpretation. Wonder what devices we're selling. Do they say? GPS devices. Okay. And then Y min and Y max, we're talking about 2,000 and 3,400. Okay, I have it in there. And you know, for the Y's, the Y scale says how often do you want to put a mark? I'm going to put a mark every 1,000. Just so we can tell where like 3,000 is. Okay, let's go ahead and graph. So you see it?
What's the line? What's the window again?
It's in the book. Right here. Right there. 0 to 40, 2,400 and 3,000. So 2,000 to 3,400. So now it says use the graph and trace capabilities to estimate an interval that will result in the n being between 2,700 and 3,000. You know, one nice way to do this would be to graph y equals 2,700 and graph y equals 3,000. I mean, remember how I did this before? I had the asymptote. What's the asymptote? 3,400, right?
32.
Oh, 3,200 is the asymptote. So I could graph that, for instance, right? There's the asymptote. But you don't want that, I don't think. I think what we want, if I go to the y equals screen again, we want to graph these values. So let's graph, it says between 2,700 and 3,000. Y equals 2,700 and y equals 3,000, or n of x in this case. And if I press graph, you see that? So now you could do some cool things. You could say, hey, between here and here, how many do you think we have to purchase? How much money do you think we have to spend if we want the advertising to be somewhere in this range, between 2,700 and 3,000? Well, he says use trace. So that's too much, right? So I start moving over. There's the upper limit. What's that say? That looks like about 3.8. What? 3.82, and these are in
Thousands.
thousands of dollars. So about $3,800 would be the upper limit that you have to spend. And then somewhere down here, well, what do we have? 1.7, right? So maybe between 1,600. So for 48, I would say spend between maybe 1,600 and what was the upper limit? Lost it. 30 what? 3,800. $3,800 because it was 3.8, right? That was x equals 3.8. And we would want to spend that much to sell between 2,700 and 3,000 devices. Guys follow? You might argue that in that part of the graph, your advertising dollars are making a big difference. In a later part of the graph, do you see how it's not so steep? Now your advertising's not helping as much. So it kind of depends. You got to know the market. That's really what this problem is about. We are out of time. That's it.